All right, so ladies and gentlemen, our objective for today is to practice doing equilibrium problems involving weak acids and weak bases. Our basic process, though, is going to be the same. Balanced equation, KEQ expression, ice table. All right, so all those things that we've been doing haven't gone away. So let's go ahead and look at this first problem. There is a typo in the PowerPoint. All right, this entire problem is involving HCN. All right, so we start with a 0.075 molar solution of HCN and measure its pH to be 5.22. We're asked to calculate two things, the Ka and the percent ionization. All right, so what we want to do, let's start with a balanced equation. All right, our acid is HCN. It's reacting with water, which is a liquid. What are the products going to be?
Cn minus and H3O plus.
Cn minus and H3O plus. Now, in Bronsted-Lowry theory, what would we call the cyanide ion? This is the base. It's the conjugate base. And the hydronium ion?
Conjugate acid.
Is our conjugate acid. All right. Could we write a Ka expression for this?
Yes.
Yes, let's do that. All right, so the Ka is equal to
H3O plus.
the cyanide times the H3O plus
Over the HCN.
over the HCN. Everyone okay? This isn't completely new to us. It's just a slightly different context. Okay, so we've got a Ka expression, we've got a balanced equation, and we need to find the Ka. So I think the next thing we should do is set up an ice table. We're going to ignore water because we know its concentration effectively doesn't change. All right. What's the initial concentration of hydrocyanic acid? 0.075. Initial concentration of cyanide? 0. Initial concentration of hydronium? 0. In order to reach equilibrium, what will happen to the concentration of HCN?
Decrease.
Decrease by how much?
X.
X. And the concentration of the products?
Goes up by X.
Will go up by X. All right. So at equilibrium, the hydrogen cyanide concentration would be 0.075 minus X, and these guys would both be X. So far, so good? All right. Now, we are actually given another piece of information. Weren't we told the pH of the solution?
Yep.
All right. Now, think about what we were doing yesterday. If we know the pH,
We can calculate the concentration.
we can calculate the concentration of
HCN.
H3O plus.
H3O plus. Sorry.
So we know that 10 to the negative pH will give us the hydronium ion concentration. Right? In other words, we're solving for X, right? So if we know the hydronium ion concentration, we also know the cyanide ion concentration. So that's what we're going to do. All right, so 10 to the negative 5.22. Plug that into your calculators. All right, if you don't have them out, you'll want to get them. All right. What did we get?
6.03 times 10 to the negative 6.
All right, 6.03 times 10 to the negative 6. That's our value for X. All right. Now, how does X compare to the initial concentration of hydrocyanic acid? It's way, 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 way smaller, right? So that's something to keep in mind, is that we're going to make the assumption in a lot of these weak acid, weak base problems, we're going to make an assumption to simplify the problems. It'll help us avoid the quadratic formula. If we assume that X is less than 5% of the initial acid concentration or the initial base concentration. All right. If X is much, much less than HA, then 0.0 minus X is approximately 0.075, right? That will simplify our math. And in some cases, this will allow us to avoid using the quadratic equation. Now, if you want to use the quadratic equation, that's always okay. But it's sometimes quicker to do this. What we will need to do is after we do our math in some of these problems, if we're solving for x, we'll need to confirm that it was actually less than 5%. Otherwise, we'll have to go back and do it with the quadratic formula. It won't really be an issue in this problem, but we want to do that. So let's solve for Ka. All right. We know x now. We know the concentrations of cyanide and hydronium ions. So that's 6.03 times 10 to the minus 6 for each of those. So we'll square that. And we'll divide by the concentration of HCN, which in essence is about 0.075. Right. So what do we get for our value for the Ka here? Yeah, I think we probably only have 2 sig figs, so 4.8 times 10 to the negative 10. Everyone good? Everyone okay with what we did? All right. Now we are asked to do one more thing. We were also asked to find the percent ionization, and this is also a classic thing that gets asked in these kinds of questions. Because we know that weak acids don't dissociate much. We know that it's going to be less than 10%, sometimes quite a bit less than 10%. All right. And of course, to use this approximation, it has to be below 5%. So to calculate the percent ionization, very easy. You're going to take the concentration of hydronium ion over the original acid concentration times 100. So easy to do. So we just plug this in. All right. So it would be 6.03 times 10 to the minus 6 divided by 0.075 times 100. What do we get for percent ionization? 0.008. So was our approximation valid? Yeah, it wasn't going to change the answer significantly. Even if we had gone back and done the calculation where we subtracted x from the initial concentration of the acid, we would have basically gotten the same answer. It wouldn't have had a significant effect. Are these okay? All right, so this is a classic kind of problem where you're given the pH, you have to find the equilibrium constant. Let's go on and look at the next problem, which is going in the opposite direction. All right, given you find the pH of clarity. All right, so, whoa, that went too far. All right, so we have a 0.45 molar solution of nitrous acid, HNO2. We need to find its pH, and we are given the Ka. You have to have enough information to do these problems. First thing we should always do, balanced equation. All right. So we'll start with HNO2, reacting with water. What will the products be?
NO2 minus.
So, NO2 minus and H3O plus. All right. And can we write a Ka expression? Absolutely. All right. So it's going to have the same basic form as before. All right. Conjugate acid concentration times the conjugate base concentration over the undissociated acid. It's always going to have that same basic form. All right. And we do know the value for this Ka. We know it's equal to 4.5 times 10 to the minus 4. Everyone okay? All right. So we do know the initial concentration of the undissociated acid. To me, this sounds like what kind of problem? Ice. That's right. Ice is always a good strategy. So this started as 0.5 molar, and these are both 0. Right? What will happen to the concentration of the nitrous acid? It will go down by how much? By x. And the other two? Go up by x. All right. So 0.45 minus x. What assumption should we make?
Less than 5%.
Yeah. We're going to say that X is less than 5%, all right? On a test paper, you might want to say, you know, assuming X is much, much less than 0.45 or 5% rule or something to indicate that's what you're doing, all right? Or even just that 0.45X is approximately 0.45. We can come back and test it later, all right? So we're going to work on this assumption that the 5% rule applies and go from there, all right? Because if we don't make this assumption, we must use the quadratic formula to solve this problem. And if we can avoid that, we'll just be happier. Right. So we always know, it's always in the back of your mind that you might need to use it, but if you could use the 5% rule, go ahead. All right. So we're going to solve for X, aren't we? All right. So we know that 4.5 times 10 to the minus 4th is equal to X squared over 0.45, because we've used the 5% approximation. All right. So now we just need to solve for X. Say that again?
0.014.
Okay. All right. Is everyone okay with X equaling 0.014? All right. So that means our hydronium ion concentration is 0.014 molar. Are we done?
No.
No. All right. What do we need to do to answer this question? Take the negative log. We know that the pH is the negative log of the hydronium ion concentration, so we need to take the negative log of 0.014. And when we do that,
1.8.
yep. Now, how many sig figs should we have in our answer?
2.
2. And remember, when you're recording pHs, the sig figs are the numbers after the decimal.
1.85.
So we want to record at 1.85. You wouldn't lose any points if you recorded 1.8. But it really should be 1.85. We want those 2 digits after the decimal place. Is everyone okay? Is this making sense? Do you see why we spent so much time developing ice problems in the previous chapter? Because we use them over and over and over again. It's really the best strategy for equilibrium. Let's go on and see if we can do the next problem. All right. Now, the next problem is a little bit different if you look at it because it involves a weak base. But before I do that, I forgot there was a slide in here. All right. There are polyprotic acids, acids that contain more than one ionizable hydrogen, right? Like H2SO3. All right. So you can write out H2SO3 forms HSO3 minus and H plus, and that would have a Ka value. And then the HSO3 minus can lose that to form SO3 2 minus and another H plus. So we can talk about Ka1 and Ka. Right? It's stepwise. Each step only pulls off one hydrogen at a time. Okay? But the only thing I really want you to know about this is that if your Ka values differ by a factor of 1,000 or more, it's the first Ka value that matters. So I just wanted to point that out to you. It probably won't come up in these, because that starts to get more involved than our level of course. But it is in our book, and I wanted to point that out to you. It's the first Ka that usually has the biggest effect. And as long as your Ka values differ by a factor of 1,000 or more, you can just focus on the first one and calculate the pH pretty well.
And if they don't?
If they don't, then you have to do multiple problems. So let's hope that doesn't show up. But I think that becomes a more advanced problem than we're shooting for right now. All right, so let's look at this problem, because this problem involves a weak base. All right, we have methylamine, which smells like rotten fish. All right, its chemical formula is CH3NH2. We have a 0.1 molar solution. We want to know its pH, and we're given a Kb value. Now, what do you think I mean by Kb? It's an equilibrium constant for a weak base. All right? So we haven't done much with the bases yet. People tend to focus on acids more, but you need to be able to solve weak base problems as well. So let's start with a balanced equation. All right? We have CH3NH2. Now, can you guys see that the NH2 part is basically a derivative of ammonia? It's like ammonia where one of the hydrogens has been replaced with a methyl group. And we know that ammonia is a base. Right? And bases accept protons. Right? So when this reacts with water, what will the products be?
NH3.
Yeah, it'll be CH3, NH3 plus, right? Because I accepted an H plus,
OH minus.
plus OH minus. All right. So this is a typical pattern for KBs. And if you guys, or for weak bases, if you look on your formula sheet, it actually gives you a generic form for how to write a KB expression and a generic form for how to write a KA expression. But you should be able to generate it even without that. All right. So let's write our KB expression. All right. It's going to be the conjugate acid, CH3 NH3 plus, times the hydroxide ion concentration over the methylamine concentration. Right. And we're given a value for this. Are we okay? So far, not too different, right? They start off all pretty much the same. Well, we've got the initial concentration of methylamine. What kind of problem is this? Ice. They're always ice problems. All right. The big thing is recognizing that. All right. So we've got ourselves an ice problem here. All right, so we've got the base, we've got the conjugate acid, and hydroxide as the conjugate base. And the initial concentration was 0.10 for the base and then 0 for the others. How will the concentration of the methylamine change? Minus X. The others will change. All right. And so the equilibrium concentration of methylamine is 0.1 minus X. What are we going to assume about X? Less than 5%. And so we're going to say that 0.10 minus X is approximately 0.10. And if X turns out to be larger than 5%, then we'll go back and solve it. But I think we'll be okay. All right. And so we can solve for X using our KB expression. All right. So we can say that 4.38 times 10 to the minus 4 is equal to X squared over 0.10. So we just need to solve for X. All right. What do we get for the concentration of the products?
0.0066.
0.0066? All right. Now that would give us the hydroxide ion concentration as well as the CH3 NH3 plus concentration. But it's really the hydroxide ion concentration that we're interested in. All right. We've got the hydroxide ion concentration now. But we're asked to find pH. Can we do that directly? No. Now there's actually a couple of ways we could go with this. I don't know if you guys have a preference either way. We developed an expression yesterday in class involving KW. Do you guys remember KW? Mm-hmm. All right. What is KW? All right. And we know that it's the hydronium ion concentration times the hydroxide ion concentration is 1 times 10 to the minus 14th. So in other words, since we know hydroxide ion concentration, we can find hydronium. All right. All right, so we can just plug that in, right? So what do we end up getting for our hydronium ion concentration? Oh, there's 2 O's in there, right? All right, say that again, Scott.
1.51 times, or 52 times 10 to the negative 12.
Is everyone okay with that being our hydronium ion concentration? So if we've got the hydronium ion concentration, how do we find pH? Negative log. Say that again?
11.8.
I would argue that it's 11.82.
Oh, I wasn't sure.
But I think
It's decimals, yeah. 11.82.
Are we good? Are these problems too bad?
Does KW change with temperature?
It does, but most of the, you'll see that all the problems will specify that they're at 25 degrees. And if they don't, just pretend you are.
Okay.
All right. So you shouldn't be worrying about the temperature being different, because you'll either be told enough information to solve the problem, so it should work out. All right. Are we good? All right. Oh, what people find is the weak acid problems are what they spend most time on. They sort of neglect weak base problems, and it's just you have just an extra step at the end to get to the answer usually, but they're very important. So I think we'll stop here.